Okay, let's dive right into this explainer. Today we're talking about smarter signals, combining MIMO and co-CFDM for next-generation mesh networks. We're going to break down the exact architecture, the multipath exploitation, and the actual physical implementation of all this in tactical MANETs. So if you've ever wanted to understand exactly how modern autonomous systems and tactical teams manage to communicate when the grid is completely down, well, you're in the right place.
To really grasp the stakes here, I want you to picture this. You're a tactical operator, or maybe you're deploying a remote robotics team. You need critical telemetry and high-definition video instantly, no delays. But standard radio signals, they just bounce, shatter, and completely fail when they slam into physical obstructions like urban canyons or dense forests. Trying to rely on a standard Wi-Fi-derived waveform or a basic single-carrier system in those environments is basically a recipe for total network collapse. So how on earth do we actually solve this?
That brings us to Section 1, the Tactical Communications Challenge. Because, let's be honest, we really can't fix the problem until we define exactly what is destroying our data links out in the field.
And that primary enemy is multipath fading. Think about it like this. If you've ever tried to hear a friend shouting across a really echoey, crowded room, you've experienced the audio version of multipath fading. As a radio transmits, that primary signal bounces off buildings, trees, vehicles, you name it. And all those echoes arrive at the receiver at slightly different times. Engineers call this delay spread and intersymbol interference. The radio waves are literally crashing into each other, destructively interfering, and just shredding your data packets.
But here is where it gets incredibly cool. The solution is a total mind-bending irony. Our most advanced tactical networks actually need those exact same multipath reflections that destroy legacy systems. It's essentially a massive engineering judo move. Instead of stubbornly trying to filter out or fight those bouncing echoes, we're going to collect them, combine them, and actually use them to multiply our bandwidth.
So, Section 2, COFDM, defeating multipath fading. To pull off this brilliant judo move, we've got to introduce our first foundational weapon.
That weapon is coded orthogonal frequency division multiplexing, or COFDM. Instead of blasting out one massive, fast, and ultimately fragile stream of data, like traditional single-carrier transmissions do, COFDM completely changes the game. It slices that wideband channel into hundreds of slow parallel subcarriers. Since each individual subcarrier is transmitting data slowly, the actual duration of each symbol is stretched way out, and that makes a signal incredibly resistant to those delayed multipath echoes we just talked about. Plus, they are spaced orthogonally. That means mathematically they are separated just enough to avoid interfering with each other, totally eliminating the need for wasteful guard bands.
Now you might be wondering, what happens if a specific frequency gets completely blocked by a concrete wall? Well, that is where the C in COFDM steps in. It stands for coded, which refers to forward error correction. The system intentionally adds mathematical redundancy across all those different subcarriers. So even if a few of them suffer from deep frequency selective fading and are completely lost in transit, it doesn't matter. The receiver can mathematically reconstruct those broken data streams just by using the surviving carriers. It's literally like sending a jigsaw puzzle where you only need 80% of the pieces to see the entire picture perfectly.
All right, Section 3, MIMO, multiplying spatial capacity. Now that we have the channel stabilized by COFDM, we can massively scale up our data capacity.
MIMO stands for multiple input, multiple output. By placing multiple antennas at both ends of the link, think of those 2x2 or 4x4 setups you see on modern tactical radios. MIMO directly leverages those bouncing reflections. The system transmits data using both vertical and horizontal polarizations. It's actually using the different spatial paths bouncing off the physical environment to squeeze twice as much data into the exact same frequency channel.
The truly crucial point here is that a smart MIMO system isn't just a one-trick pony. It dynamically switches its entire strategy based on what the environment throws at it. If the link is struggling and pushing the edge of its range, the system uses antenna diversity. It sends redundant, identical signals across multiple paths purely for survival, giving you a much better signal-to-noise ratio. But if the connection is rock solid, it instantly switches to spatial multiplexing. It treats those bouncing paths like parallel data lanes on a highway to literally double or quadruple your maximum speed.
Moving to Section 4, the MIMO-COFDM synergy. This is where we see how these two technologies build into an absolutely unstoppable combination.
Here's exactly why they are the perfect pair. MIMO technology inherently requires what engineers call a flat fading channel to process its spatial matrices effectively.
The problem, of course, is that real-world environments are messy, wideband, frequency-selective nightmares. But remember what CoFDM does. It takes that messy wideband channel and slices it up into hundreds of tiny, stable, flat-fading subcarriers. Because CoFDM neutralizes all that messy delay spread, MIMO's digital equalization algorithms can step right in and calculate spatial matrices independently and flawlessly for every single one of those tiny subcarriers. So what does this synergy actually yield in the real world? Well, the data shows that implementing this multi-stream MIMO spatial multiplexing increases the peak payload bitrate by over 112%, over double. And what's truly remarkable is that this massive leap in capability only requires a tiny 1.5 watt increase in power consumption. Think about that for a second. For battery-powered autonomous drones or dismounted soldiers, getting more than double the throughput for almost zero power penalty is an absolute game changer.
Which brings us to Section 5, Real-World Tactical MANETs. Let's look at how this theoretical physics actually operates out in the dirt.
You know, there is a really stark contrast between commercial and tactical architectures. Commercial IoT networks, like cellular LPWANs, they rely entirely on a centralized star topology. They absolutely need fixed cellular towers, and they typically only offer sub-megabit throughput. Our tactical mesh networks are a totally different beast. A MIMO-COFDM mesh is fully decentralized, it's self-forming, it pushes well over 100 megabits per second, and crucially, it requires exactly zero existing infrastructure to function.
But with all these powerful nodes dynamically moving around a battle space, how do they avoid just screaming over each other? Standard Wi-Fi uses a contention-based system where everyone just listens and tries to talk when it's quiet. In a dense mesh, that leads to massive collisions. So instead, advanced tactical systems use a chronological token passing mechanism. The network generates a digital token that passes sequentially between the nodes. A node can only transmit its data when it physically holds that token. This completely eliminates the transmission collisions and the self-interference that basically break standard consumer networks.
And routing data through this incredibly fluid network requires immense intelligence. You can't just count how many hops it takes to get from node A to node D, because the shortest path physically might be a terrible, lossy link right through a concrete bunker. So instead of just counting physical hops, these smart nodes analyze live RF telemetry. They use a cross-layer metric called ETX, or expected transmission count. The network mathematically measures the forward and reverse packet delivery ratios to route data through the absolute most reliable, highest bandwidth path available at that exact millisecond.
And this isn't just theory anymore. We see this exact architecture deployed successfully right now. Industry standard bearers like Silvus Technologies with their MN-MIMO waveform and DTC with their MeshUltra tactical COFDM mesh have operationalized this science. They're packaging all this intelligence into highly robust 5-watt transceivers operating at bandwidths up to 20 megahertz. Make no mistake, these aren't consumer Wi-Fi chips. These are purpose-built radios giving autonomous connected vehicles, robotics, and tactical teams the penetrative power to stream crucial data without ever needing a direct line of sight.
All of this leaves us with a genuinely fascinating question to wrap up our explainer today. We've seen just how effectively this architecture conquers the absolute harshest tactical environments. But as we look toward the future and the rollout of 6G networks, engineers are heavily exploring decentralized, self-free massive MIMO for everyday civilian use. So how long until the multipath judo and decentralized routing that we've perfected for the battlefield completely reshapes our global cellular infrastructure? Could this finally eliminate dropped calls and cell edge interference for good? It's an incredibly exciting frontier. Thanks for joining me to explore this